Hi. Hi, I am Luca Bartolomei from Vision for Robotics Lab at ETH Zurich. In this work, we present a full pipeline for multi-robot coordination with an agent-server architecture that allows autonomous robot navigation in partially known environments. In time-critical situations, such as in disaster scenarios or search and rescue tasks, multi-robot systems are preferred over single robots, as they can accomplish missions faster. They are also employed in other use cases, such as patrolling, thanks to their flexibility with respect to vehicle fault. For instance, if one of the robots in the team cannot continue, the others can adapt to the situation to complete the task. Multi-robot systems are growing in popularity in the research community, but to have a complete multi-robot solution, high requirements have to be fulfilled. In fact, coordination between the agents, as well as the capability of co-localizing the robots in the same map, are crucial. In literature, there is still a lack of practical approaches, as unrealistic assumptions are made. Generally, perfect knowledge about the robot states is assumed, as well as non-global maps. However, co-localizing the agents in the common reference frame is far from trivial, as state estimates are subjected to drift. Additionally, perfect previous knowledge is not possible in general, as only partial information is available. The recent work by Kuznets et al. At FSR 2019 is the closest to the system here presented. There, the authors introduce a multi-robot planning framework for persistent coverage. However, they do not deal with the problem of co-localization. Instead, in this work, we present a complete multi-robot pipeline for unmanned aerial vehicles, or UAVs, that proposes a solution covering both co-localization mapping and planning and coordination. Our pipeline is composed of a central server and a team of Our pipeline is composed of a central server and a team of N agents. We assume some prior knowledge about the navigation area, for example from aerial imagery. Given this prior information, we select the area of interest and we assign to all the agents in the team a series of goal positions, which are also communicated to the server. Every agent is assumed to be equipped with GPS, visual inertial sensors, and a wireless module to enable communication with the server. Every agent is assumed to be equipped with GPS, visual inertial sensors, and a wireless module to enable communication with the server. The server performs the most expensive tasks, such as multi-robot sensor fusion and global planning, while on board the agent, only visual inertial odometry or VIO and local obstacle avoidance are required. In the following, we present the pipeline in more detail. Assuming GPS and a stereo camera equipped with an IMU are available to every agent, the images and inertial sensor measurements. Assuming GPS and a stereo camera equipped with an IMU are available to every agent, the images and inertial measurements are used by a keyframe-based VIO algorithm to estimate the go motion of the robot. In our experiment, we use a modified version of Vince Mono. The stereo images, instead, are processed to obtain a local map of the surroundings as a point cloud. These point clouds are compressed, and, together with the GPS measurements, the current odometry The point clouds are compressed, and, together with the GPS measurements, the current robot pose and associated keyframes, which include 3D image keypoints and the 3D landmarks from the VIO estimator, are communicated to the server. The server performs optimization-based sensor fusion in the PostGraph backend by fusing the sensor measurements from all the agents to co-localize. The server performs optimization-based sensor fusion in the PostGraph backend by fusing the sensor measurements from the agents to localize the robots in the global reference frame. The server performs optimization-based sensor fusion in the PostGraph backend by fusing the sensor measurements from the agents to localize the robots in a global reference frame. Using the results from the sensor fusion, the point clouds are used to build Using the results from sensor fusion, The compressed point clouds are used to build a global dense map of the environment, which is used by a hierarchical multi-robot global planning. Using the results from sensor fusion, the compressed point cloud are used to build a global dense map of the environment, which is used by a hierarchical multi-robot planner to generate global paths that are communicated back to the agents. These paths serve as input to the local planner that generates smooth collision-free trajectories using the local map previously built. The same connections are repeated for every agent in the team. Notice that the same connections are repeated for every agent in the team. Notice there is no data flow between the agents, as all the communication goes through the server. In the following, we focus on the Postgraph backend in order to give a better overview of how the system In the following, we focus on the Postgraph backend in order to give a better overview of how the sensor fusion component works. We will later focus on the planning. We will later focus on the planning components. The objective of the Postgraph backend is to localize the agents in a global GPS reference frame W, which is unique across the robots. We indicate every agent I with reference frame S and the VIO estimates with TOS. This transformation is subjected to drift. We model this drift using the transformation TMO, where M represents the agent's drift-corrected map frame. Finally, we use the transformation TWM to retrieve the agent's pose in the global reference frame W. The same kind of concatenation is repeated for every agent. The same concatenation is repeated for all the agents in the team. The Postgraph backend optimizes the transformations here highlighted in red to estimate the poses of the agents in the global reference frame W and to eliminate the drift coming from the VIO estimators. To fulfill this objective, VIO, GPS, and point cloud information are stored in a Postgraph structure where every node contains different elements: GPS measurements, keyframes containing the robot's pose, HD key points, and FD landmarks, which are later used for visual loop closure, and finally the local point clouds. These point clouds are not used for localization, but they are just anchored to a node to generate a global map after Postgraph optimization. The Postgraph is built incrementally for every agent. Every time a new keyframe is inserted in the graph, a local optimization over the n last inserted keyframes is performed. The point clouds are not used for localization, but they are just anchored to a node to generate a global map after optimization. This postgraph is built incrementally for every agent. Every time a new keyframe is inserted in the graph, a local optimization over the n last inserted keyframe is performed. The same procedure is repeated for every agent, where after insertion of a new keyframe, the local optimization is triggered over the n last inserted keyframes. In order to constrain the robot In order to constrain the poses of the robots with respect to each other, we check for visual loop closures over the whole graph. Upon the detection of a loop closure, both within an agent's trajectory and across multiple agents, we perform global pose optimization. The objective is to refine all the poses and the transformations in order to get globally consistent estimates. From the optimized pose graph, we can then estimate the agent's poses in the GPS reference frame W. Additionally, using the optimized poses and the corresponding dense point clouds, we can generate a global dense map using the VoxBlocks framework by Oleneikova et al. The poses of the agents and the global maps are then used by the multi-robot global planner to coordinate the motions of the UAVs. The planner computes the path for the agents toward their respective goal positions using the RRT star algorithm. To avoid collisions amongst the robots, we use a hierarchical approach. At startup, we arbitrarily assign To avoid collisions amongst the robots, we use a hierarchical approach. At startup, we arbitrarily assign priority levels. To avoid collisions amongst the robots, we use a hierarchical approach. At startup, we arbitrarily assign priority levels to each agent. Then, we proceed to plan the path for all the agents following this hierarchy. In the example, we plan the path for Agent 1, avoiding collisions with the obstacles in the map. To plan the path for the second agent, we consider the area around the path of Agent 1 as a no-fly zone. The path computed for Agent 2 is to avoid both the obstacle and the navigation area of all the other robots with higher priority. The planning then continues along this line until all agents in the team have been processed and all the waypoints have been reached. Upon completion of the mission, the UAVs return to their respective home position by planning in known explored space. Every time a new global path is computed for one of the agents, it is communicated from the server to the corresponding robot, which follows it towards the goal. However, as global paths are generated in the global reference frame W, they are first transformed into the local odometry frame O. Using this rough path, the local planner generates trajectories Using this rough path, the local planner generates trajectories using the uniform B-spline formulation introduced by Usenko et al., which considers the UAV's dynamics and performs obstacle avoidance. In the following, we present the evaluation of the pipeline. To evaluate the performances of the Postgraph backend, we use the EUROC dataset. To simulate GPS, we use the available global poses. To simulate GPS, we use the available global position measurements by disturbing them with Gaussian noise. In the table, we report the average absolute trajectory errors of the estimations. In the table, we report the average absolute trajectory errors of the estimations over 3 runs. In the first column, we present the performance of VIO only, obtained from comparison. In the first column, we present the performance of VIO only, obtained from the comparison between the ground truth trajectory and the estimation from VIO. In the second column, instead, we show the error between the robot ground truth and the trajectory as estimated by the Postgraph backend after optimization. It is worth noticing that the backend is able to reduce the drift in the estimation. In the last column of the table, we evaluate the accuracy of the transformations from the global reference system to the map frames for all the agents. Given the Postgraph estimate for one agent, we align it to the ground truth using the last estimated transformation TWM at the end of the mission. This evaluation shows Given the Postgraph estimate for one agent, we align it using Given the Postgraph estimate for one agent, we align it with the ground truth using the last estimated transformation TWM at the end of the mission. This evaluation shows that the error is only marginally increased when compared to the previous results, indicating a high accuracy of the estimated transformations. Finally, we showcase the complete pipeline in a series of experiments in photorealistic simulation of an industrial environment. In the first experiment, we showed the exploration of the industrial area using 4 UAVs. The robots and the corresponding waypoints are highlighted with different colors, while the VoxBlocks map is represented as a gray mesh. The waypoints were selected in a lamb-mower pattern in overlapping areas of interest. All agents successfully reached the waypoints, discarding any ill-placed goals. During the experiments, we ran the backend and the global planner on the central server, while visual inertial odometry, local obstacle avoidance, and control ran on separate PCs, all connected to the same network. After completion of the mission, all the agents returned to their respective home position by planning global paths in known explored space. In the second experiment, we showcased the advantage of the proposed centralized architecture. Since a dense map contains all the agent's experiences, parts mapped by a robot can be reused for planning by another one. In this video, it is possible to see how the red agent planned its path through the alley, which was previously mapped by the green robot. The mission then continues until all the agents reach their respective waypoints and return to their home positions. In the last experiment, we present the proposed hierarchical approach for multi-robot global planning. Here, the agents with the highest priority is in red, followed by the green and the blue robots. The goal positions for the three agents are placed within the same navigation area. The agent with the highest priority plans straight line trajectories, while the other two UAVs have to compute intertwined paths. Nonetheless, all agents are able to reach the assigned goal positions, avoiding collisions amongst them and with the obstacles in the map. After completion of the mission, all the agents return to their respective home positions. To summarize, in this work, we designed a multi-robot coordination framework for UAVs to be employed in search and rescue missions, dropping some of the typical assumptions made in multi-robot planning literature. We extensively evaluate the system in simulation, and we demonstrate it can guide the navigation of a team of UAVs, ensuring no collisions amongst the robots and within the workspace. We extensively evaluate the system in simulation, and we demonstrate it can guide navigation of We extensively evaluate the system in simulation, and we demonstrate it can guide the navigation of a team of UAVs, ensuring no collision amongst the agent and with the workspace. Additionally, the source code of the pipeline will be made publicly available at beforerel.ethz.ch. Future research directions will investigate the automatic assignment of waypoints for the agents to minimize the human intervention in the pipeline, and how to reduce the dependency of the system on external sensors, such as GPS. Finally, since the computational load in the current pipeline increases with the number of agents, we will investigate how to improve the systems Finally, since the computational load in the current architecture increases with the number of agents, we will investigate how to improve the system in terms of scalability.